Hello all, welcome back to this course, Design of Fixed Wing UAV. So we considered airflow, which is nothing but ordered motion of this air, and we have represented the flow by means of this ordered motion by means of these straight lines called streamlines, right? So what are these streamlines? By definition, we can say it is the path traced by the fluid element to which tangent at any point represents the direction of velocity vector. So what does it mean? Let us say if I draw the path traced by the fluid element in this particular fashion, then say at this particular point, consider a fluid element, a small fluid element here, let its position be here, and then if you draw a tangent to this, so at this particular point, the velocity, the direction of the velocity of this fluid element is horizontal, almost horizontal along this particular line. So if you look at this particular point, it is the tangent is more or less in this particular direction to this curve. So this gives you the direction of velocity of this fluid element. That is, it is going forward and downward, right? So at this particular position, it is going up. Say this is the tangent here. So this is the velocity, direction of this velocity vector. So if we consider a fluid element here, so this gives the tangent here gives the corresponding direction of this particular fluid element here. The streamline itself is the tangent here, so the direction of velocity vector is along this particular lines. So let it be v infinity. What we considered is so in our previous class to find out velocity is we considered a steady streamline flow, and say let A be the point in the free stream which is far ahead to this particular sensor, right? So this particular sensor or this particular measuring unit, we call it as pitot tube, and there is a static tube around this pitot tube from which we measure the static pressure. Let PS be the static pressure. Say this static pressure is measured by means of holes on the periphery here. We made this tube to interact with the free stream by means of these holes, and this total pressure is measured by means of this pitot tube. Let P naught be the total pressure measured here. So the incoming fluid element, which is at point A, have this free stream conditions with the pressure P infinity, velocity V infinity, is brought to rest isentropically. Say this particular fluid element is brought to rest isentropically at point B, called the stagnation point, and the corresponding pressure is P naught, and the velocity at this particular point is 0. So from here we are able to deduce using Bernoulli equation. What we deduced is P naught minus P infinity upon half rho infinity, where rho infinity is the density. So if you know the differential pressure and the corresponding density, will be able to figure out what is velocity here, right? Pressure and density and temperature is a function of altitude. So from which we have derived this gradient layer equations and isothermal layer equations, where P2 upon P1 in a gradient layer is equals to T2 upon T1 raised to the power of minus G0 by AR, right? And rho 2 upon rho 1 is equals to T2 upon T1 raised to the power of minus G0 upon AR minus 1, where A is called lapse rate, dt upon dh, which is Kelvin upon kilometer. So, and also we have come up with isothermal layer equations. Where there are constant temperature zones in which we assume the temperature is almost remain constant in that particular layer. So for any 2 points in that particular isothermal layer, we can relate using these 2 equations. E raised to the power of minus G0 by RT times delta H, with delta H is equals to H2 minus H1, and R is equals to 287 joule per kg Kelvin for air, right? So we have used these 2 equations and solved one example problem where we want to find the velocity of the aircraft at 12 kilometers altitude, where we are able to measure the total pressure. Is that what it is given, right? So, and we have solved using the geopotential altitude. So let us now look at what happens when we create a pressure difference. So we have ambient conditions here, like the atmospheric conditions here. Let us assume we create a sudden pressure difference. Can you give one such example? Let's consider a fan. When you switch on the fan, what happens immediately? You start feeling the wind, right? Some stream of air. That's because the fan is creating some pressure difference here. Right? Let us assume this is one such disk called an actuator disk. Let us say this is called actuator disk. So this is called actuator disk, which is capable of creating pressure difference. Let us say this is the upper surface, or let us say to the right, pressure to the left, and this is pressure on the right side. If I take this is my left and this is my right, so I'll label them as pressure on left and right. So this actuator disk, let us assume the thickness is minimal or very small, and let A be the cross-sectional area of this disk. Let capital A be the cross-section area, or area of this disk, simply area of disk, right? So what happens when there is a pressure difference here? What exactly the fan does? It will try to draw air from backside, and it used to throw air at us, isn't it? So, but let us assume, seeing it is trying to, this particular disk is trying to draw the air from ahead of it and try to throw it behind it, right? So in fan it's a reverse case, right? It will draw air from behind and throw it ahead. So it's a reverse case here. And so let's now first look at far ahead. Let us say if I place a fan here, so somebody who is sitting at 100 meters from here, is he going to feel any difference because of this, right? So definitely no, most likely no, with the ordinary fan that we generally use. So let us say at far ahead, so let us say this particular at far ahead, we this disk, which we call it as an upstream of this disk, what we have is the atmospheric conditions, which is P infinity is 1 atmosphere here. Let us say this is station 1 that I am considering. And far downstream of this, say again, if I stand behind 100 meters of this fan, do I feel that any difference because of it? So let us say this is my station 2, which is again at atmospheric pressure conditions. P infinity is equals to P atmospheric, right?
Here
Which is 1 atmosphere here. What we can read there is static pressure, right? So, but here at some distance, this has come close to P infinity, which is atmospheric pressure here, and then, yeah, so far ahead I don't, so the velocity is 0. Right? And these two particular lines represents the boundary conditions of this, are nothing but the stream lines which are on the boundary or the circumference of the stream tube. What is stream tube? If we have a bunch of these stream lines together, then we can consider it as stream tube. Right? So at station 1, I have P naught, P infinity, and V is 0. And at station 2, this disk is inducing certain velocity to this flow. So which is nothing but Vi here. Let Vi be the induced velocity induced to the flow because of this disk. Right? And let V2 be the velocity at the station 2 where pressure is equals to P infinity, and then let A2 be the corresponding area, this particular stream tube, cross-sectional area of this stream tube here, right? So for this A to be 0, this has to be infinite, close to 0, let us say. This has to be, the area here of this stream tube to be very high, right? So now, now let us look at, so what we know is about the pressure here, right? So let us see how the pressure is varying here. So if this is the location of the disk, right? So what's happening initially, say this is my static pressure or P infinity, which is atmospheric pressure. So it drops as we go close to this disk, isn't it? Let us say this is the location of this disk, right? So at this particular location, so it drops, the pressure drops, the PU, the upper surface, so sorry, the left pressure to the left of this disk is dropped, right? And then there is a sudden increase. Why? Because here there is an induced velocity here, isn't it? What's happening? See, in this particular portion there is no addition of energy, isn't it? So according to Bernoulli, what happens? If the pressure from static condition, it is now converted to the pressure, some static pressure plus dynamic pressure here, isn't it? Because the flow is set into motion here, and it is moving. So almost close to this disk, it is ahead of disk. Let us consider it is moving at a velocity Vi, and we consider it is thin. Right? So this velocity remains constant across this particular section here, right? Why? Because the area of the disk is very minimal here. So according to continuity equation, this velocity remains constant across this particular disk. So what's happening? We are imparting some additional energy, right? This energy increases the pressure here, right? And then so the nature will take care of the rest once you have increased the pressure here. So now the air or the fluid which is at high pressure tries to accelerate so that the pressure the raised pressure becomes equal to the ambient conditions, right? So here, so it is trying to get back to this. So let this be P on right side pressure, which there is a discontinuity here, right? Now let's see what happens to the velocity. So we know that so let's say this is the initial velocity, or say it is at rest. Now So this is V infinity. So this is at rest at station 1. Say this is my station 1. This is the disk and this is my station 2. So what happens here? The velocity increase to Vi and we don't know what's happening after that, isn't it? That we'll see. So the pressure, there is a sudden increase in pressure because of this disk, and this pressure needs to be equal to the ambient condition after certain distance, like downstream of this disk, right? In the slipstream, then the slipstream has to, in the slipstream, this particular air has to, if the pressure has to drop, right? Then it has to accelerate. Am I correct or not? Within this particular portion, again there is no addition of energy. Only at this disk there is an addition of energy here. So within this particular portion we can still apply this Bernoulli's principle. So P plus half rho V square is constant. So if P has to drop down, dynamic pressure has to increase. Right? So let's see, will it follow that or not? We'll derive that. So the velocity increases. So what do you think is the variation of total pressure? So till disk it is P naught is constant, and at the disk there is a addition in P naught. Right? There is an addition in pressure because of this particular disk. This is the total pressure here. Fine. So let's now look at the mathematics. So again, we are trying to look at what a pressure difference does to this particular disk, right? So what's happening here? The air is pushed back by this propeller disk, and according to Newton's third law, so the air will also push, right? How it is pushing this disk will be in the opposite direction, right? So what that push must be equal to? So there is a force because of this pressure difference across this particular disk, right? So what is the pressure difference? P on right minus P on left times the cross-sectional area of this disk, or the area of that disk. Is it not? This is the force with which the air is pushing this disk forward. So let us say this particular force is known as T, which is thrust, right? Where T is the thrust acting on the disk, right? For example, if I rigidly hold this disk, rotating disk, I will also experience the same force T, right? If it is more than my frictional force, right, isn't it? So then I will try to move in that particular direction. So T is thrust here, right? So let's say this is our equation number A617.
A15. A15.
Sure.
A15. Yeah. A15.
This is our equation A15. And so what's happening here? So there is a force that is generated here, right? Isn't it? Because of the flowing mass of air. Am I correct or not? So this mass of air is entering this stream tube at a velocity V0, right? And leaving this stream tube at a velocity V2. That means there is a change in momentum. This change in moment is what is going to create this force. Am I correct or not? This can also be related by this. So m dot at station 1 times velocity at 1 minus, otherwise m dot at station 2, right? So this mass flow rate is due to this disk, rotating disk, isn't it? So this disk is what creating that mass flow rate. So what is that value? Mass flow rate is equals to rho A V, right? M dot times, sorry, V2 minus V1, let us say. So what is V2? So V at velocity at 2 minus 0, right? Let V2 be the velocity at this particular location. So, okay, second station, this is V2 at station, this is at V1. Am I correct? Okay. Let 0 be the velocity with which this mass is entering this particular stream tube. What we have is rho A. So the mass flow rate is due to this disk. So at this disk we can have rho A V dot. Rho A V is the mass flow rate m dot, where A is the area of the disk, V is the velocity induced in the disk, times this velocity V2. Right? This is the thrust generated because of this mass flow rate, right? A change in momentum. Right? So now equations A15 and A16 represents one and the same thrust that is being generated. Am I correct? Now let us also look at what is. So according to, let me just note it down. So what we have is P plus half rho V square is equals to constant, right, along a streamline here. Okay. Now let's look at this mass conservation here. So it should be rho A Vi should be equals to rho A2 V2, right, which is equals to A Vi is equals to A2 V2, where V2 is the velocity measured when P is equals to P infinity here. Right? The static pressure equals to P infinity. Okay. Now let's apply Bernoulli's equation ahead of the disk and behind the disk, because here there is an addition of energy which we can't use, because of which we can't use this Bernoulli equation throughout this, right? We can use it in this section 1, or section 1 is given, so part A, section A and section B, right? So what we have here is P infinity, which is the static pressure, and the velocity here is 0, right, is equals to velocity to the left side of this disk, which is PL, just immediate to the disk, and then the corresponding dynamic pressure is due to the velocity, induced velocity Vi, right. So okay, so similarly, if you apply this Bernoulli's equation to the part B, right, so from A, from B, what we have is PR plus half rho Vi square is equals to P infinity plus half rho V infinity square, sorry, V2 square. Okay. Okay. So just remember this A15 and A16. We'll call back these equations. So using these two equations, what we have is subtracting these two, this A equation from A, from equation B, right? So what I have is PR minus PL is equals to PR minus PL is equals to half rho V2 square. Let us say this is my equation 18, A18. Now comparing this equation 18 and then previous 15 and 16, what we can write is the thrust generated here, or so T is equals to P left minus P, or say P right minus P left, right? What was there? P right minus P left times the area, isn't it? Which is equals to Which one?
Above equation, A16.
This
Sorry,
one.
A17.
This one is A70.
Oh,
Yeah. So PR minus PL times A is equals to rho A VI times rho A VI times V2. Right? Using 16 and 17. So using 18, what I have is, so VI is equals to, or say V2 is equals to 2 times of VI. So using equations A15, A16 and A18. Right? Am I correct or not? Okay, so V2 is twice the induced velocity here. That means the flow is accelerating here, right? And what will be the cross section area? A2 here. So using this particular A17, we can relate using A17. What we have is, so A2 is equals to 2VI, A upon 2. So half the cross section area of this, half the area of the disk. So area of this cross section area of this twin tube is half the area of this disk. That is why it is accelerating, right? So
yes.
yeah.
It is.
So let this be A19 and A20. Fine? Clear? So we can also express this induced velocity in terms of this thrust loading. That's also a good equation to note it down. So from this 15 and 16 again, using equation 16, using equation A16, what I have is T is equals to V2 to rho A VI square, right? Since V2 is to VI. So this implies, so the corresponding induced velocity depends upon root over T by A, right? So this particular factor T by A is known as thrust loading. So what is the amount of force generated across this particular area of this disk, right, is known as thrust loading, right, which is Newton upon meter square. Yes, yeah, too many equations, yes, I can understand, but still we have to note it down. So VI here is the induced velocity by this disk depends upon this particular thrust loading factor, right? And how much power we need to spend in the first case, right? How much power we need to spend in order to create so much thrust. So is it clear? Is my question clear? So that means if this disk is generating thrust T, that means this disk is also pushing the air with the same force, but in the opposite direction, right? And it is pushing that air at a velocity Vi, isn't it? So the power induced, or the power that we need to put in, is equals to power induced is equals to thrust times Vi, right? Am I correct or not? The force times the velocity. So what are the units of this power? Which is watts. In watts. So this equation be A22, right? Fine. So that means in order to generate a thrust T, I need to produce this much of pressure difference, right, across a disk of cross-sectional area A. And if I produce this much of thrust or this much of pressure difference, it creates a velocity at a downstream where the pressure equals to P infinity, right? So it induces a velocity of twice that of induced velocity, right? It accelerates the flow at this particular velocity, right? So it is worth noting down non-dimensional analysis or non-dimensional parameters for this particular actuator disk theory, right? So with which we will be able to compare propellers of various configurations. Okay, so what we are dealing with is Frod's momentum theory or actuator disk theory, right? So that is what we are discussing here. So we know now this thrust will propel your aircraft, so will take your aircraft forward, right? Given if it overcomes the resisting forces, isn't it? So this is the main idea. So thrust is this is how we can generate thrust. This is one of the means with in which we can generate T to accelerate our aircraft. Now let's look at some non-dimensional parameters. So if I had to compare propellers of different dimensions and different geometric characteristics, right? If I have to compare them with, to bring them onto a single platform for comparison, I need certain non-dimensional parameters, right? So let us first look at, so one important factor that we look at is the induced velocity here, right? Let's define a non-dimensional induced velocity, which is lambda I is equals to Vi upon Vt, where Vt is the tip velocity, velocity at the tip of this disk, right? So V keeps varying. Am I correct or not? Induced velocity keep varying along the disk. So Vt remains constant for a given propeller. Okay. Not at a particular RPM again. Okay. And then let's define Ct is, so non-dimensional induced velocity so lambda I keep varying along the radius of the disk, right? As we progress towards the tip, this lambda I keep varying. Okay. Whereas Vt remains constant for this particular RPM. So similarly, let us now define thrust coefficient. Which is Ct is equals to T upon dynamic pressure, right, times the area of the disk. So dynamic pressure times the area will help you to, like this is force upon force, helps you to non-dimensionalize this thrust, right? So this V is nothing but, again here is the tip velocity here, fine, where Ct is called non-dimensional thrust, which is the thrust coefficient here, right? And now can we rewrite this equation? So can we look at this equation? So what is Vi? So Vi is equals to 1 upon 2 rho, right? So let me do this. Let me rewrite this equation. So root over T upon rho A times 1 upon root 2. So what I can do this with this is like Ct by 2 Vt square, isn't it? Root over Ct by 2, which is 4 times Vt square. Right? So this equals to lambda I root over Ct upon 2, or Ct is 4 lambda I square, right? E23. Where is other equation? So let this be 24 and this be 25, right? So can we also convert this? So similarly you can do this. So let's say Cpi is defined as Pi upon half rho Vt cube times area, right? Similarly you can relate them. So you can substitute this in this particular equation, and then for T again you can convert it in terms of coefficient Ct. You will be able to arrive at this particular non-dimensional pressure coefficient Cp. Okay, Cp is or pressure coefficient, which is a non-dimensional number, which is pressure, induced pressure coefficient. So this is the amount of power that you need to, sorry, it's not pressure coefficient, power coefficient. I'm sorry. Cp is the induced power coefficient, which is Pi upon half rho Vt cube times corresponding cross area of the disk. So Cpi is the power coefficient, which is the induced power coefficient. So you need to spend so much of power in order to throw the air at this particular velocity with the thrust 3 backward here, right? So what we can observe here, pressure difference across a disk created a force called thrust in the forward direction. Say if that forward direction is nothing but the direction of our motion, then if you hold, or say if you fix that particular setup rigidly to our aircraft, then the aircraft will also move with a thrust 3, right? Will also experience thrust T in that particular direction, right? So later on we'll again come back to that point, right? So we'll solve an example about this particular momentum theory, and then we'll get back to that, how thrust is going to help us, right? So let's solve a small example. So this is our next example, A4. Example number 4 in this introductory topic. So consider the data of a brushless motor with propeller tested on a bench, right? Which was tested on a bench, let us see. Tested on a bench, right? So the data corresponds to the slipstream measurements. What are these measurements? So P in the slipstream is equals to 1 atmosphere, and V in the slipstream is identified as 20 meters per second, right? And these measurements are effective within an area of say 0.0707 meters square. Okay. So these are the measurements here. So what do you mean from this slipstream measurements? So we have say a BLDC motor, brushless motor, right, which is rigidly mounted on a bench, and we have a propeller have a propeller here. So this is mounted on a bench by means of an adapter. Okay. This is the bench, and we have a propeller here mounted on this motor, and so when the propeller is operated, when this pre-LDC motor is operated, the propeller rotates, due to which there is change in downstream conditions here, right? And it is identified at a far downstream. So let us say this is my particular location at which P is equals to 1 atmosphere, that is measured here, and then V is equals to, so static pressure here, right? Yeah. Okay, and V infinity is equals to 20 meters per second, right? 20 meters per second, and the corresponding area of effectiveness is about 0.707 meters square. Okay, now what do we need to find? So find the thrust generated by the motor and first one, find the thrust generated by the motor and propeller combination. So when we have these measurements, what is the corresponding thrust generated by this motor and propeller combination? That's what we have to find. And the second one is, what is the change in total pressure due to this BLDC and propeller combination. And also power required to generate this thrust. Fine. So these are the three questions that we need to answer. Straightforward, right? So let's assume the interference is negligible with the flow. So with this setups and all. So with this attachment and the rest of the setup, let's assume that they are not going to interfere with the flow here. Find the thrust generated by the motor and the propeller combination. So with this information, so V at this particular station is about 20 meters per second. So what I can do is, like, we know the relationship between this VI and V, isn't it? So what is VI here? VI is V at this particular station is 2 times that of VI, because the pressure is 1 atmosphere, right? So VI is equals to 10 meter per second, right? So V is 20 meters per second, so what VI is 10 meters per second. Similarly, once we have this, I know what is AI times VI at this particular disk is equals to A times VI, A times V at this particular location. So area of disk and area at this section, let us say this section 2 in our case, right? So A2, let us say this is A2 here, right? So A2 times this particular V2 here, or V infinity, whatever. So VI, so what is A here? So VI upon, A by 2, right? A2 by 2. So 2 times A2, right? Isn't it? So V2 is 2 VI, so it becomes 2A2, which is, what is the area here? So there is a small correction here. Let's consider this as 0.0353 meter square, So what we have here is area is equals to 0.0707 meter square. So this is the area of the disc. Am I correct or not? So if I have to know what is the thrust, please make this correction here. So the area of this disc, stream tube at this particular location is equals to 0.0353 meter square. So which is approximately, so here using this relationships, so we figured out that the area of disc is approximately 0.070 meter square. So the thrust generated is equals to PR minus PL times the corresponding area, right? So how can I get it? So you can do this way, or you can also, since you know what is VI, you can, right? You can use this, you use the thrust formula, but I am not doing that. You better do this. So far ahead of this is equals to atmospheric pressure, like, right? P infinity, which is far ahead of this disk, is equals to PL plus half rho VI square, isn't it? So PL is equals to P infinity minus half rho VI square. So what is the value here? So this is 1 atmosphere, which is 1.01325. So because far ahead of this disk is again 1 atmosphere, and the velocity there is 0, right? 10 to the power of 5 Pascal minus 1.225 times 100. So what I have here is 1. Similarly, I can find out what is the pressure on the right side of this. This is the pressure on the left side of the disk. And to the immediate right of the disk, what I have is PR plus half rho VI square is equals to P infinity at station 2 plus half rho V2 square, which is, let's say, this is my station 2, right? So what I have here is, so what is PR is equals to P infinity at station 2 is 1 atmosphere, then 1.01325 multiplied by 10 raised to the power of 5 plus 0.5 times 1.225 times V2 square minus VI square. So this is like 400 minus 100. So the answer here is PR. So the pressure on the right side of the disk, immediate right side of the disk, is Pascal. Right? So substituting these numbers, we can get the corresponding thrust, which is equals to, so 1.5 approx 1.015 by 1 minus 1.00126 times 10 power 5 times 0.030 0.707, right? 0.707. So the thrust T is equals to, which is 17.666 newtons, which is close to 1.7 kg. This is a thrust generated by this particular engine. Okay. So this is the thrust generated by this engine, and the corresponding power generated is equals to power required is equals to thrust times the velocity, which is 176.6 watts. So this is answer for the third question. This is answer for the first question, right? Am I correct? So what is the change in the total pressure? what is total pressure ahead of the disc? Right. Total pressure ahead of the disc is nothing but atmospheric pressure here, right? So 1 atmosphere, and total pressure behind the disc is PL plus half rho V square. Am I correct or not? You can see that PL, so PR plus, PR plus half rho V square. You can see the so pressure on the left side has dropped below the atmospheric pressure, isn't it? It's P infinity minus this particular quantity, and P on the right side, like it's like, yeah, P infinity plus the total, yeah, increase in the velocity. Is that P on the right side, right? So this particular quantity is the total pressure on right side, and this particular quantity is the total pressure on, so P infinity is nothing but 1 atmosphere, which is the total pressure on the left side, right? So the change in the total pressure delta P naught is equals to PR minus P on the right side, P naught R minus P naught L, which is 1.0151 times 10 power 5 plus 0.5 times 1.225 half rho V square, right? PR plus half rho V square. Half rho VI is 10 meters per second, 10 meters square, minus 1 atmosphere, 1 ATM, right? This is equals to 246.25 Pascal is a additional pressure that is added because of this particular disc. So the power required to generate this thrust is close to 177 watts here, right? Okay, thank you.